All right, let's go ahead and get started. Greetings, everyone, and welcome in to my channel. I am Professor L, and this is the live stream for math um, help math tutoring. Just going to have the stream here, and I'll be here for a good 30 minutes at least, minimum. Unless something else happens. And that's the goal, is to get to at least 30 and then not to overdo it. So if you have a math problem you would like to see me attempt to work out, you are welcome to put it in the chat, and we'll just play it by ear. And in the meantime, I'm going to be working on my board, and I decided to go ahead and try to, I'm going to continue talking about the exponential function, um, but I'm going to go ahead and sketch the graph of the logarithm function, because the logarithmic function actually is the inverse to the exponential function. And so I thought it would be cool to kind of show the symmetry, and then recall that identity function line, and how the inverse functions have that symmetry along the identity function line. So we'll pull it back to a concept that I brought up last month, and we discussed before, and I'll be able to get my ruler out. I like to get the big ruler out on the board for some reason. I think it's cool. So I hope everyone's doing well. And if you are watching and you know anyone that needs some math help, you might want to let them know that I'll be here for a little bit, working problems on my board, and just hanging out. And I've dedicated this time between 6 and 7 p.m. Central Time to do math and hang out and work with students. So it's any problem is fair game. It's just that I can't guarantee if it's too difficult, I'm obviously not going to be able to work it. So I will do my very best. And so a couple things, because I'm trying to make the most of this platform and this space and this time, I want to make sure that I'm reflecting on things that I feel like yesterday was a complete, it's really scary to watch you make a mistake and then you haven't fixed it yet. And I'm glad I caught that, because that's a kind of a big deal. With the growth and decay models, you have to have an initial starting value. So A has got to be, well, A can't be 0, but and A can be a fraction. It can be any number as long as it's not 0. But B has to be greater than 1 for a growth, and then between 0 and 1 for a decay. And I'm glad I caught that, because that's kind of a big deal for this function. And really, we haven't talked too much about the exponential function. I haven't discussed any applications or any complicated graphs. We were just basically visiting one of the general graphs or just the basic graph of the exponential function, and then the translations in the graph. So we looked at 4 of them, and here, and so that's pretty cool. But we didn't get into anything too technical. We didn't use we used a couple of the exponential laws. At maybe a future date, we could possibly get into some exponentials, but right now I'm just trying to, in my spare time, I'm trying to focus on the graph. So maybe we can come back and look at the math later after I get more familiar in this setting. But for now, we're just going to be focusing on the math required to actually sketch the graph by hand. And yeah, that was kind of a little caveat that I wanted to go ahead and reflect back on my mistake before I erased it. Because I am going to go ahead and erase, yeah, we'll erase everything. And yeah, start thinking about what I want to do to graph this logarithm function. And well, logarithms, they're kind of different. They it's such a foreign abstract notation for logarithms. The way they're notated in the rules that most people, you know, unless you are someone who really likes math, you're probably looking at logarithms like, you know, completely foreign, something that's, you know, something's not understood. I don't know what the word is for it right now, but yeah, logarithms. But once you discover the notation and what's going on with this logarithm and you become more familiar with it, you realize how useful it is. And one of the favorite applications, but there were so many. There were so many decibels of sound, use logs, and I'm thinking of the applications that I visited with using logarithms. pH is a big one. Measuring pH and calculating pH based on values is a big one. But yeah, some of the applications of logarithms, but there are many, many, and in math modeling, it's a big function. And so, and one of the main reasons why I'm deciding to discuss a logarithm, so we'll just start out with y equals log a of x. Well, the main reason why is because it is an inverse to the exponential function. So you have the log function, and then its inverse is y equals a b to the x. So if you were going to rewrite this one in exponential form, you could use the exponential form of this graph, and it would look like this. A to the y equal x. And then you could use that to convert your values. So I am going to use, so we'll look at y equals, and we'll leave a 1, and we'll say b is 3. And so we're not drawing exactly the same graph as yesterday, but we'll say 3x, and then its inverse. We're going to also graph, and I'm going to put it, am I already erasing? That's funny. All right. I'm going to erase this and put it here. A to the y equal x. And, or I'll put it, let's scoop this whole thing over. Y equal log a x, a y equal x. Yeah, that's what I want to say. Okay. So basically what this is saying is this is log base a of x. So so the answer to the logarithm is the degree it's the exponent that I have to raise a to obtain x. So x in the argument is basically the answer to this exponent, if that makes sense. So here's the unique relationships. Like this is the base, and this is the answer to the exponent, and then y is actually the exponent that it's raised to. So this is what log is calculating. What it's returning to you is the exponent that this base must be raised to obtain x. And so I know I just explained that the best I could, and I'm gonna sit and repeat myself. But since the graph, I know that they're inverses, I'm going to pick f of x to equal log 3 of x. And so what I'm doing is I'm just going to graph the inverse function. And I was thinking about how I want to go about this, because knowing their inverses, all you have to do is swap out the domains and ranges of these two functions. And I have to have another table here. I'll go ahead and sketch it in here now. Going to have to evaluate this function, and then I could just swap the domains, or I could go ahead and try to evaluate the function. So let's go ahead and get the Cartesian coordinate system out. And I want to go ahead and sketch the graph of my exponential function here, because I know I have to do that one already, and it's not as ugly as the logarithm. I mean, it's pretty ugly, and I don't mean like ugly, like bad looking. I just mean it doesn't look fun. It doesn't look pretty. And it's a lot of the notation is just what you got to get used to. So when we figured out what we were doing, and then after I did it several times, I'm like, oh, okay, this is the method. It wasn't that big a deal. But logs, I haven't seen them in a while, so I'm looking at them like, ooh, how would I evaluate it if I didn't know that these were inverse functions, and that they would have, I could just swap the domain and range. So I'm going to go ahead and take this one through, I think -3, right? -3. And then we'll go, I don't know if I want to do that many. Okay, we'll do it. -2, -1, 0, 1, 2, 3, and see how fast we can evaluate this function. And then, yeah, because I'm just playing around. And another caveat here, minor, is that, I know it's live, and I'm probably making a fool out of myself sometimes when I make mistakes, but for some reason I decided to do this, and it's important, and I'm not gonna just stop. So anyway, we're gonna go ahead and pick values and go ahead and label our values here. We'll keep them kind of close this time. So this is -3. All right, see how far we'll have to go out. We'll say -1, -2, -3, and then -1, negative. Here I go. And this is part of me not being comfortable in front of the camera. So the more I do it, I feel like I'm getting a little bit more comfortable. So go ahead and put some values here for our range. And we're going to go ahead and evaluate this function starting, we can start with -3. Since we already did this yesterday, and so it's a similar process, but it's a different function. So we'll just say, we're going to change this one to f of x. F of x, because y equal f of x. So I'll go ahead and just do this here and try and see how small I can keep the math. So we go f of -3 is going to be 3 to the -3. And that is 1/3 cubed. So we do not want to go out to 3 because that's a big number. 3 times 3 is 9, times 3 is 27. So we are going to, or wait, that's 1/27. Okay, I'm good. That's a really small number. Okay, 1/27. 1/3 cubed, which is 27. That's not a big deal. So we'll keep it. -2. F of -2 is 3 to the -2. This is 1/3 squared. So this is 1/9. I act like I haven't done math today. And it's just probably because it's so late, And math, I think the best part of the day to do math for anyone is first part of the day. Maybe not first part, but like after you've been awake for about an hour, it's ideal. All right, so we've got 3 to the -1, and just keep looking to make sure I'm not covering what I'm writing, because, all right, so 1/3. That's tragic when I notice I do that. So we've got these 3 points, and let's see, f of 0 is going to be 3 to the 0 power. Anything raised to the 0 power is the quantity 1. So it's pretty straightforward that if it's not going to have a different a value, then this value is going to always be 1 here. I've noticed that trend. And then f of 1 is 3 to the first power, which is just 3. And then it's going to get really big really quick. It's going to go to 27. So f of 2 is 3 squared. And that is 9. And then one more in here, f of 3 is going to be 3 cubed, which is 3 times 3 times 3, which is 27. And you can kind of see the symmetry here. All right, so -3, we've got 1/27. That's a really small number. That is very close. 1 divided by 27. 0.037. So I'm just going to put it right above. I'll make it big. A little tick mark in there. That's a really tiny number. And then -2 is 1/9. So that's probably 0.10 right there. So just a little bit bigger. And that's not even doing it justice. And then -1 is 1/3, which is probably just a little bit more. But it does start gaining momentum by the time it hits the 0 line, because by the time it gets to 1, or the 0 line, it's already at 1. So it gains rapidly. It starts out going staying real close to 0, and then when it hits the 0 for some reason in the positive values, when x is greater than 0, that's really where the party is at for this function, and you get to see the growth and the decay. So we've got 1, 3, 2, 3. So what is that? 1, 3, it's here. And then we've got 2, by the time we get there, we're already at 9. Yeah. 5, 6, 7. I knew I was going to do that. All right, look. I think that did it. 7, 8, 1 more, 9. All right. All right. I just had to get that last point in there. It was so important. All right. So we've got our exponential function here, sketch. All right. And I really wanted to dash that, but that's okay. We'll go ahead and just label it. So this is f of x equal 3 to the x. And for the okay, you really see it take off after it gets to 0, but over here in the negatives, it's just hanging out. It's coasting right above that 0 line there in the x-axis. Well, if I wanted to sketch the function of log and I was just being lazy, I could just swap out the domain and the range. Nine, 27. So I would have these points appear in my domain, only positive, of course, because the logarithmic function, that thing that we talked about, or I talked about yesterday, where if you notice where this graph lives, it only lives when y is positive. So like I was talking about yesterday, and I put these quadrants up here. Quadrant 1, you've got x positive and y positive. And over here in quadrant 2, you have x negative and y is positive. And then quadrant 3, you've got them both negative. And then quadrant 4, x is positive and y is negative. So what happens is you have this symmetrical graph where it's split in two, where the top half of this graph, you have the y values are positive, and the bottom half, the y values are negative. So what that means is that no matter what value you plug in the domain, and the domain of this function is all real numbers, and it's a parentheses negative infinity to positive infinity. But you have a problem here because the function does not go negative, you're going to have a domain issue. It's never going to approach 0. And the reason that is because you're not ever, whenever you go to solve for your intercepts, so when you take your function here, y equals 3 to the x, and I plug in for when x is 0, the y-axis is this x equals 0 line, because no matter where you are on that line, x is always 0. So if I want to know what my graph is doing, where my graph exists when x is 0, I need to only plug in 0 to the function to figure that out. And when I plug in 0 for 3, I get 1, because 3 to the 0 power is 1. And so that is my y-intercept. So that is my y-intercept. But when I go to find my x-intercept, and I repeat that process to find my other line where it's crossing here on the x-axis, this line right here is the y equals 0 line, because no matter where you are on this line, y is always 0. So when I go to try to plug in the same concept and let y equal 0, I have this problem. Oops, because I have what exponent. So when I go to answer this to solve this, what I'm looking for is a value for x, which is an exponent that I can raise 3 to obtain 0. And there's not one. There's not one. So it leads to only positive values just above 0. And there are not any negative values in this graph. So that matters, and that is a good segue into the logarithm, and the reason why you're only going to have positive values in your domain is that the logarithm cannot, it's because of this fact right here. You cannot put, and you see here, you have this thing going on. You have 0 equals 3x, and here you have 3 to the x equals 0. So you notice that x is 0 here. You cannot put 0 in the argument. If you do that, it will give you a domain error, because logs, you cannot have a 0 or a negative, and they have to be greater than 0, this value here. But if I were lazy and I just wanted to sketch the graph of a logarithm really quickly, I could just do this. I could swap out the domains and the ranges and see what's going on with this graph. So that's going to be a 1, 2, and a 3. Well, okay, good. So we're going to go ahead and sketch those points. 1/127 and -3. Let's see what that is. So we're going to need some negative values in here. So we'll say that is 1, 2, 3. That should be sufficient because we're only going to -3. So this would be 1/2. So this is probably real close. We're just going to say it's right there. 1/27 -3, so it's right there, just above that. It's not touching the y-axis, it's just sitting right next to it. And -2 1/9, it's a little bit further, not much, really hasn't moved much at all. And then, oh wait, hang on. 1/9 -2, okay. Then 1/3 is going to be slightly less than 1/2 over here. So we'll say that's about 1/3. And it says 1/3 is -1. Here we are. A little bit further. And then it says at 1, 0 is my intercept. Right here. And then look up 3, 1. So here's 3, 1. And we have some points that are too big because I'm not going to be able to see. I can make it out to 9 here, but we still we're able to get the behavior of this curve here. So we've got this thing going. We have 3, let's see. 5, 6. Yeah, almost, but what it's doing is it's going that direction. So we got close. We'll just stop it there. And then it's going like that. And then if we wanted to sketch the graph of that identity function line, see if I can get enough points and get my handy dandy around. Let's see if we can see that symmetry. And I feel like I cheated a little bit because that was really easy. So I want to go back and see if I can evaluate, at least evaluate some of these points and find them without the use of the knowledge of the inverse functions. Okay, yeah, it looks pretty good. And so inverse functions, rather, no matter how complicated they all follow that symmetry about the identity function line. So we'll go, excuse me. I cannot believe I sneezed on camera yesterday. That was really embarrassing. Oh, that's all right though. That's what you do. You put yourself out there. All right, so I'm going to go ahead and label this f of x equals, and this was log 3 of x, and then this one is f of x equals x. So we have all 3 of those on there. And the log function, okay? So we cheated, all we did was swap points. Let's see what happens if we try to evaluate one of these. Let's go ahead and put so you can't put the negative values in the domain. You can only put positive values in there. So up to 0, you couldn't list those same values. And you notice in the graph over here that the function's not existing. It doesn't start existing until it gets over here on the other side of 0. And it only lives where x is positive. So you can only put positive values in the domain. So we'll only start with the positive ones. So we'll just start with 1. And so this would be f of x. So it'd be f of 1 equals log 3 of 1. And then basically the way that I solve that is I prefer the change of base. So this both puts it into base 10. So this is log 1 over log 3. And then what could you do? Since it's base 10, it'll be log 1 minus log 3. Well, anyway, and then you'd probably have to put that in the calculator because I think, and this has been a long time ago, but I'm pretty sure they had math textbooks used to have um, indexes where they would have like, and I know statistics books still have like z-score tables, and you would probably have to go through. They have tables where they have all these values printed out in textbooks before internet and before the use of like tools and like calculators and stuff. Before they had like how did you tell the calculator? How did you program the calculator to figure out logarithms? And well, they probably just stored the tables. I'm not sure how they did it, but anyway, we can just figure this out. So we have log 1 divided by log 3, and it's saying it's 0. Log 1 of log 3 is 0. Yes, it is. It's 0. F1 is 0. Good. I don't know how. I do not know how, to be honest. I maybe at one point in time I knew a lot more and was very well rehearsed in logarithms, but just full transparency, it's been a while. And I just realized I've already been talking for more than 30 minutes, so I better get on with it. But it says it's 0. I want to try one more and see what happens. So let's try another one. So let's do f of, well, we know what the answer is, but we'll go ahead and try f of 2. F of 2. So this is going to be log 3 of 2. So using the change of base, log 2 divided by log 3. Let's point here and see if it gives me a fraction. Math 1. No, 0.62240. Hang on, get the calculator out. Oh, I can't figure out. I'm so tired today. 62240123118. And what I'm curious is, it's not on there. but it's gonna be in between 1 and 3. So we have to calculate 3 now. We'll have to do f of 3. I should have done f of 3. I don't know why I picked 2. Log 3 of 3. Oh, huh. It's the log of 1 rule. So you can also look up the log. I looked up the log rules, but there's also the log of 1. If your base and your argument are the same, that is equal to quantity 1, and that checks out with the change of base, because if you have log 3 over log 3, anything divided by itself is equal to 1. So good, that one checks out. Okay, all right. Yeah, so I'm pretty satisfied. I think that if I did one more, this one would lead to some of this, like, rules that I could use to simplify. And that may be what I talk about tomorrow. I'm really just trying to play it by ear and familiarize myself with the camera and the setting, and just see where it goes. So just taking it day by day, and yeah, not trying to be too presumptuous. Yeah, and trying to not get burnt out, even though I'm doing it 5 days a week. I've been toying with the idea of maybe not doing it on Friday anymore. I maybe just go down to 4 days a week. We'll just see. But for now, I'm having fun with it, and I feel like that I'm nowhere near running out of content. There's always seems to be something that I think of too so far, and so um, as long as I'm, I guess, willing, able, and available, I'll go ahead and continue doing the same schedule. But yeah, we'll go ahead and call it quits for today, because I'm over 30 minutes now, and I don't have any questions. So yeah, if you are watching my video, thank you so much. I really appreciate any of the support that I get in the platform. And if not, maybe you know someone that needs help with math, and or anybody who likes math that wants to come hang out and do math with me. That would be awesome. And maybe let's see, I'll think of something that is relevant and helpful for students. And yeah, I'll just go ahead and stop rambling on and go ahead and end the stream. And so I hope everyone has a wonderful rest of your day. And if you want to hang out and do some math with me, I will be back tomorrow at the same time and same place. So bye for now.